Yes, apparently you lost, but I think you are not too sad to be here. So, you know which one it is?
It's A.
This one. I'll let you the chair here. So that
yeah. Okay. Oh, I can. Okay, so I will give two examples of monitoring of structures, and these examples are from offshore domain. So I also saw some offshore pictures yesterday by Helmut. He was also involved in some offshore project. But the objective is firstly to address the short and long-term effects of measurements, and not the least the long-term effects, because you have to do processing of the data and you have to come up with reduced uncertainties on the model variation, the model predictions. Also to illustrate the examples, which are riser angles at the flex joint and also ship in Arctic areas. And also when it comes to prediction of future loads, that will also, not the least, fatigue damage of the structural components. So for the riser monitoring example, we have typically that the original design parameters are no longer valid, so we have larger BOPs, blowout preventers, larger vessels in harsher weather, and also we have more BOP days. That means you have more days in operation for the systems we're looking at. We have increased utilization of each well. And also the attention to wellhead fatigue has increased over the past 2 years. So what is a flex joint? This is now the lower part of a riser. We can see we have the BOP and we have the lower flex joint, LFJ, and this is like a hinge, so it can tolerate angles, but also it will transfer forces to the lower part of the riser and the wellhead, not the least. And the wellhead is critical for containing the pressure on the well. If you destroy the wellhead, you have a blowout. So the consequences could be like the Deepwater Horizon, with a lot of pollution and a lot of delays. So we know the cost of the Deepwater Horizon accident was tremendous. So you can easily imagine that the cost of a monitoring system is outweighed by the potential cost of a failure. So for the calculation models, you subdivide the marine riser and wellhead models. So you have a global model of the marine riser, then a local model of the wellhead and soil interaction to predict what's happening in this local area and the fatigue damage accumulation. So this is now the measurement system. You have some components down at the flex joint and you measure the angles. And based on the angles, we can also predict the forces acting on the lower part of the riser, not the least the wellhead. So this is you have cables essentially, so you need to transfer the signals by cables to the surface vessel. So based on the angles, you predict the loads, and then you predict the stress ranges and the fatigue damage accumulating. So the question of long-crested waves, you can see from this measurement, it's shown on the upper right and the lower left. We have random motions of the vessel, and this will transfer to the motions, to the angles at the lower part of the riser. And you can see we have varying directions of the sea states. Also you have like a random process in along two axes, two angles. So you have a bivariate Gaussian process. So that means you need to divide this into sectors, and for each sector you can predict the contribution to the fatigue damage. And then you sum around the sectors that you observe during the measurements. So on the projecting planes or the sectors, we can find the standard deviation and do cycle counting, also rainfall counting, and we can estimate the damage, fatigue damage during the measurement period. So now this is a global model of the riser. It's based on the computer program RIFLEX from Marintek, and you see we have different stiffness properties. Essentially it's B model, but in the upper part you have quite special boundary conditions. You have a constant tension because you have a heave compensator. The vessel is moving, but you don't want the riser to move with it. So that means you have tensioners that will keep the riser in a more or less fixed position, but then the vessel is riding on this top of the riser, and you have a so-called tension joint on the upper part. Also, the lower part, you have a linear versus nonlinear flex joint, so that means you have potentially nonlinear components in the system based on the variation of the stiffness with the angular displacements. So we can see that also the boundary condition on the soil has influenced the soil stiffness, because the wellhead can move if the soil is not perfectly rigid. So you have a flexible spring at the lower part of the model. This is now the full-scale long-term angle distribution. So you have 2 months measurements, and you have the cycle distribution. So this, of course, will help you in predicting the fatigue damage. Cycle, we see the high cycles are few, and the low amplitude cycles, there are many. So that means you can fit by a Weibull distribution, and that is typically applied in offshore. You have Weibull distribution of the cycle stress ranges. So also spectral densities. There is some funny phenomenon. We can see we have 3 consecutive hours, and the first hour you have mainly response on the wave frequency regime, but then during the last third hour you have more slow drift motion, that is very low frequency motion, so you have some second order variation of the hydrodynamic loading on the vessel. That means you have frequency spectral change during these 3 hours, so you have to be aware that you have not constant frequency range for the excitation, and that also gives influence on the fatigue cycles. So we can see also the bandwidth parameter distribution. This is now the bandwidth of the process. So bandwidth parameter 1 means you have a very wideband process. You have like almost white noise or approaching white noise, but then 0.5 and less, you have more narrow band process. But we can see we are mainly in the wideband range, so that means you need to also use the rainflow methodology to predict the fatigue damage. Now we can also see we have a response spectral comparison, and we have 2 peaks in response spectral density. So this is now obtained from the numerical model. So we can see that we also have 2 peaks of the spectral density, but we don't predict the low frequency response, because that's not included in the analysis at present. We could include it by having drift coefficients for the vessel, but presently it has not been done. So this is, of course, some future work to be included. Now comparing long-term distributions, this is now comparison between the measurements and the simulations. So we see we have the red and blue are the numerical predictions, then the black dots are the full-scale data, and again we see the lack of prediction of the low-frequency stress ranges, so that means the numerical models have to be updated to include the low-frequency regime also. Now, with standard deviations, you can get quite good agreement on the energy in the signal, because even if you miss some low frequency ranges, you can still get the total energy more or less correct. So we see that if we have a so-called the green line, Torsetaugen spreading, a nonlinear spring, we have quite good agreement with the full-scale measurements, which are the black line. So and the dashed lines are plus minus 2 standard deviations as compared to the measurements. So you can get quite good agreement on the response energy. Now this is also if you use the updated model based on the best prediction, you see we get better agreement between the full scale and the measurements, but still there is a little bit energy missing in the low frequency range. So conclusion from the riser monitoring, that you have made comparison between the standard deviation of the cycle distribution for angular response, and you can also include more realistic conditions and narrow the gap between full scale and measurements wave spreading, weather direction, material properties, nonlinear flex joints. But we also see that the low frequency motion should be addressed to have a better prediction of the very high amplitude but very few cycles. But when it comes to fatigue, what really contributes is mainly the intermediate range, because we have multiple cycles at that range, and the low cycle, high amplitude cycles do not give so high contributions to the fatigue for the present descent curve that we are applying. Now, second example, this is from a ship. There was an expedition in 2007, and this is a Coast Guard vessel operating in ice, Coast Guard in Svalbard Islands. And this was a project performed by DNV, and there was also a subcontractor doing the instrumentation on the vessel. So we got access to the data. This figure to the left shows hopefully you can see it, it's fiber optic cables. So they are glued to the stringers in the hull. This is now the stiffeners in the hull. It's not the plating, but it's internal stiffeners. So it's like a secondary strain estimation, and then you have to predict the ice loading on the hull based on what you measure internally in the hull. And of course, these were mounted not in the Arctic, but at the mainland, probably maybe in summertime, so people didn't have to freeze the fingers to mount these sensors. At least I didn't have to freeze my fingers. Because I received the data afterwards. And we also see that we have the frames in the bow, because the bow takes most of the beating in the ice. So you have 6 sensors in the bow, and then you have 1 sensor on the side of the hull. But the main loading was observed in the bow region. And this is the route of around the Svalbard island. This is far away from the mainland of Norway. It's more like in the Russian Arctic. Russians also have some bases on Svalbard, but it's coal mining run by a Norwegian company. So this vessel was traveling around the islands in different ice conditions in 2007. And also, when you measure the strains on the stringers, you have to estimate the loading, the red arrow to the right, so you can estimate the differential loading on the frames. So that means you can also estimate the ice loading acting along the hull. So that is the fast assessment. You can also do finite element analysis and back calculate the loading for given strains you observe. So this is just some details of how you can compute the loading. It's F, which is the force that you calculate. Now, this is now an example of recordings of the ice pulses. So we see they arrive like in clumps, so they have very short durations. And I'm also told they make a terrible sound on the hull when you travel in ice. For these small vessels, you really have a lot of sound and vibrations from local plating due to these ice peaks. So this is now the travel distance and the time. And then you ask, what is the statistical model for the amplitudes, the peaks of this process? And it's like a Poisson process, but the amplitudes still are varying, so we need to have a distribution for that. So we are using statistical inference. This was a PhD student doing the analysis of these measurements. And then we can see that this is typically two-slope population, so you have, it seems that the high values of the loading is driven by some maybe multi-year inclusions in first-year ice, so it is harder ice, which is driving the upper part of the population. So it is like a breaking point where you have changing the slope or the distribution. So frequently traditionally, people have been using one-slope curves, Weibull or exponential distributions, but we found if you have a 2-parameter exponential or 3-parameter with 2 slopes and a mixing coefficient, then you get better agreement with the observation. So this is what you see with the green line here. We have a generalized model which is based on proportional combination of 2 1-parameter exponential models. So this is to be able to predict extreme values more accurately than if you have a one-slope model. So it reduces the model uncertainties in the calculations. So this is just to show the expression in mathematics, and also you can estimate the parameters as function of ice thickness, because as you change the thickness, you also change the parameters of the ice load population. So this is just to show the ice thickness is on the horizontal axis, and then you have the 3 parameters on the vertical axis in this figure. So also we can predict extreme values by subdividing these measurements in different periods. So you can subdivide in 1-minute intervals, take the maximum value in each interval, and then you can use extreme value statistics to tell what is the largest load in a given duration based on the initial peak distribution. You predict the extremes based on that. So you can also apply type 1 Gumbel distribution, which is frequently applied offshore also for ice loading. And this is now comparison between the different models. You have exponential, 1 parameter exponential to the left. We see that the high values are under-predicted by the model, and also the Weibull under-prediction. The 3 parameter exponential in figure C gives good predictions. Asymptotic, also a high extreme value for the peaks, is not very good, but the 3 parameter exponential is found to be the best, at least for this data set. Yeah, this is now prediction of the extremes. You have 2 different methods. I will not go in details on that, but essentially you have the yellow. This is the 1 parameter exponential prediction. You have the blue-green, which is, or I would say blue, that's the Weibull, and then you have the one to the right, which is the 3 parameter exponential. So we see that the other models would under-predict the extremes, and these 2 algorithms, they give comparable comparisons of the 20-year extreme, which is typical lifetime for a ship hull. So we see that there is a significant under-prediction by using the other models, so that means knowing that you have an improved statistical fitting gives you more accurate prediction of the extreme values, loads which will act on this hull. This hull is robust, but the system is intended for other types of vessels like tankers traveling in ice. That means you will have different ice classification. This is an icebreaker, so it has a very high ice class, but you have also other vessels, merchant vessels with lower ice class. So of course to predict the extreme ice loads would be important to avoid damage to the hull and also failure and leakage. Time is okay? Or, okay. Yeah, okay. So there are 6 models compared, and this is just to show the model uncertainty on the extreme value statistics. So we have Weibull, 3 parameter Weibull for 2 different approaches. So both approaches give roughly the same extreme value. So to conclude on the ice load measurements, we have looked at the initial apparent distribution of the ice load peak process, short-term extreme statistics of the ice load. Also long-term extremes can be obtained because you have condition on the ice thickness. So if you know ice thickness predictions for a given area, you can extrapolate to long-term extremes like 1 year or multi-year operations in ice. We also looked at fatigue damage prediction. I did not include that in this presentation, but there are some papers which have been written on this topic where we also have looked at the fatigue models for the same vessel. And you see the black dots on the ice, that is the people from the, this is now a ladder. The vessel is resting at the moment. It was a scientific expedition, so these are now people relaxing on the ice. So this was also, there have been later campaigns afterwards to do measurements in this region with ice loading. So concluding remarks overall, there is increased application of instrumentation technology because you have more ready to go instruments. Also, you can perform them both online and offline. So this system is intended for the ship, is intended for online also advice to the captain. But also you see, have seen that we have offline and long-term predictions. We have illustrated application different types of structures, and also, not the least, it's important to identify which failure modes you can address based on the given monitoring system, because a given system cannot solve monitoring of all potential failure modes of the structure, and this is very important to be aware of. If you look in this direction and the failure is in the other direction, you should be aware that the monitoring system is not the solution to all kinds of failure mode assessment. So, yeah, and then acknowledgements. Co-authors, also company 4Subsea for making RISA response data available, and also DNV knowledge for making strainer measurements from KV Svalbard available for public publications. So, thank you for your attention.